ಇವಾಗಾದ್ರೂ ಸ್ವಲ್ಪ ನಾವು ಹೆಂಗ್ ಈ ಸೈಡ್ ಇಟ್ಟಿತ್ತಲ್ಲ ಸೊ ತೋರುದಿಲ್ಲ ನೋಡಿ.
ಅದೇ ಅದೇ ಈಗ ಇನ್ನು ಆ ಪ್ರಾಬ್ಲಮ್ ಬರ್ಲಿಕ್ಕಿಲ್ಲ. ಈಗ ಸರಿ ಆಗ್ಬೋದು. ಈ ಸೆಷನ್ ಮುಗ್ದಾದ್ಮೇಲೆ ಗೊತ್ತಾಗುತ್ತೆ ಎಂತ ಕತೆ ಅಂತ.
ಒಂದ್ 5 ನಿಮಿಷ
ಈಗ ಸರಿ ಬಟ್ ಇದು ಜಸ್ಟ್ ಕ್ಲಾಸ್ ರೆಕಾರ್ಡಿಂಗ್ ಮಾತ್ರ ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್ ಇರ್ಬೇಕು ಅಂತ ಇಲ್ಲ ಅಲ್ಲ?
ಇಲ್ಲ, ಅದು ಮೊನ್ನೆ ಅಬ್ರಾಮ್ ಬರ್ಮನಿಗೆ ತೋರಿಸ್ಬೇಕಿತ್ತು.
ಸರಿ ಸರಿ ಸರಿ
ಆವತ್ತು
ಓಕೆ ಲೈವ್ ಇದೆ ಅಲ್ಲ?
ಈಗ ಅಂದ್ರೆ ನೋಡ್ತಾರ
ಅದು ಗೊತ್ತಿಲ್ಲ, ಹಂಗೆ ಹೇಳಿದ್ದಕ್ಕೆ ಇದು ಮಾಡಿ ಇಟ್ಟದಷ್ಟೇ. ಸರಿ ಮಾಡುವ ಅಂತ ಹೇಳ್ತೀವಿ.
ಬೋರ್ಡ್ ಸರಿ ತೋರುತ್ತಲ್ಲ.
ಇದು ಸರಿ ಇದೆ, ಇದು ಹಿಂಗಿರ್ಲಿ ಈಗ ಸದ್ಯಕ್ಕೆ.
ಅಲ್ಲ, ಇದು ಮೊನ್ನೆ
ಅದೇ ಇವತ್ತಿದ್ದು ಈ ಸೆಷನ್ ಮುಗ್ದಾದ್ಮೇಲೆ ಹೇಗಿದೆ ಅಂತ ನೋಡೋ.
ಅಲ್ಲ ಸರಿ ಇರ್ತದೆ. ಮೊನ್ನೆ ಅವತ್ತಿನ ಫಸ್ಟ್ ಡೇ ನಂದು ಆಗಿಲ್ಲ, ರೆಕಾರ್ಡ್ ಮಾಡಿದ್ರೆ ಆಗಿರ್ಲಿಲ್ಲ. ಸೆಕೆಂಡ್ ಡೇ ಯಾವ್ದೋ ಒಂದ್ಸತಿ ಮಧ್ಯಾಹ್ನ ಕ್ಲಾಸ್ಗೆ ಯಾವ್ದೋ ಒಬ್ರು ಕ್ಲಾಸಿಗೆ ಹಾಗೆ ಆಯ್ತು. ಮೋಸ್ಟ್ಲಿ ಸುಖಾನ ಬರೀ ಸರ್ ಕ್ಲಾಸ್ ಇದೆ. ಇದು ಮ್ಯೂಟ್ ಅಲ್ಲಿ ಇದೆ.
ಓಕೆ ಓಕೆ,
ಕ್ರಾಸ್ ಚೆಕ್ ಮಾಡಲಿಲ್ಲ. ಸೊ ಝೂಮ್ ಮೀಟಿಂಗ್ ಮ್ಯೂಟ್ ಅಲ್ಲಿ ಕಾರಣ ಕೇಳಲಿಲ್ಲ.
ಓಕೆ ಓಕೆ,
ಒಂದ್ ಸೆಷನ್ ಹಾಳಾಯ್ತು.
ಅದು ಬೈ ಡಿಫಾಲ್ಟ್ ಮ್ಯೂಟಿಗೆ ಹೋಗುತ್ತಾ?
ಬೈ ಡಿಫಾಲ್ಟ್ ಮ್ಯೂಟ್ ಹೋಗ್ತದೆ. ಅದು ನಾನು ಅರ್ಜೆಂಟ್ ಅಲ್ಲಿ
ಅದೇ ಚೇಂಜ್ ಮಾಡ್ಬೇಕಷ್ಟೇ. ಕಾನ್ಫರೆನ್ಸ್ಗೆ ಸರಿ ಮಾಡಿ ಇಟ್ರೆ ಆಯ್ತು. ಈಗ ಇನ್ನು ಮಾಡುವಾಗ ಇರ್ತೀರಾ ಕಾನ್ಫರೆನ್ಸ್ ಟೈಮ್? ಇರ್ತೀರಾ?
ಅದೇ ಅದಕ್ಕೋಸ್ಕರ ಬಂದು ವರ್ಕ್ ಫ್ರಮ್ ಹೋಮ್ ತಗೊಂಡ್ ಬಂದಿದ್ದೆ.
ಇವರು ಹೇಗಿದ್ದಾರೆ ಅಪ್ಪ? ಉಮಾಶಂಕರ್
ಇನ್ನೂ ಐಸಿ ಅಂತ ಹೇಳ್ತಿದ್ದಾರೆ.
ಇನ್ನೂ ಐಸಿ ಇದ್ದಾರೆ.
ಅವರಿಗೆ ರೀಸನ್ ಗೊತ್ತಾಗ್ತಾ ಇಲ್ಲ.
ಎಂತ ವಿಷಯ ಅಂತ
ಯಾವ ರೀಸನ್ ಆಗಿದೆ ಅಂತ
ಅದು ಗೊತ್ತಾಗ್ಲಿಲ್ಲ ಇನ್ನು.
ಗೊತ್ತಾಗ್ತದೆ.
ಅದಕ್ಕೆ ಅಬ್ಸರ್ವೇಷನ್ ಎಲ್ಲ ಇಟ್ಟಿರ್ತಾರೆ.
ಕೆಲಸ ಇದೆಯಲ್ಲ
ಇದು ಹೋಗು, ಅಪ್ಪ ಕರಿತಾ ಇದ್ದಲ್ಲ. ಈಗ ಸ್ಟಾರ್ಟ್ ಆಗಿದಾ ರೆಕಾರ್ಡಿಂಗ್? ಮಾಡ್ತಿರೋ
ಎಡಿಟ್ ಇವಾಗಲ್ಲ, ಆಮೇಲೆ ಶಕ್ತಿ ಮಾಡ್ಬೇಕಷ್ಟೇ. ಆಕ್ಚುಲಿ ನಾವು ಕ್ಯಾರಮ್ಸ್ ವೆಬ್ಸೈಟ್ ಇದೆಯಲ್ಲ, ಈ ವರ್ಕ್ಶಾಪ್ ಮಾಡಿ ಎಲ್ಲ ಈಗ ಯೂಟ್ಯೂಬ್
ಅದು ಫೋಟೋ ಸೆಕ್ಷನ್ ಅಲ್ಲಿ ಇದೆ, ಫೋಟೋ ಸೆಟ್ ಇದರಲ್ಲಿ ಇದೆ ಸೆಟ್ಟಿಂಗ್ಸ್. ವಿಡಿಯೋ ಇಲ್ಲ, ವಿಡಿಯೋ ಮಾಡೋದು ಬೇಡವಾ? ಇಲ್ಲ, ರನ್ ಆಗ್ತಾ ಇಲ್ಲ. ಇಲ್ಲಿ ವಿಡಿಯೋ ಅಂತ ಬರ್ಬೇಕಲ್ಲ?
ಇಲ್ಲ, ಇದು ಒತ್ತಲಿಲ್ಲ ಅಷ್ಟೇ, ಟೈಮರ್ ಒತ್ತಲಿಲ್ಲ.
ಈಗ ಓಕೆ, ರೆಡ್ ಬಂತಲ್ಲ, ರೆಡ್ ಆದ್ರೆ ಲೇಸರ್ ಅಲ್ಲಿ ಇದಾಗುತ್ತೆ, ರೆಕಾರ್ಡ್ ಆಗ್ತದೆ. ಈಗ ಓಕೆ,
ಅದೇ ಇಲ್ಲಿ ಟೈಮರ್ ಅನ್ನು ಕೇಳಿದ್ರೆ So today what I try and do is to show some results. In around for various applications to M matrices going back to Gauss seidel or Gauss Jacobian convergence, and then connected to what we were introduced to earlier. So we begin with do you have any questions before any questions? Looking at just trying to write this theorem. I'll directly and prove as much as possible, but this theorem is beyond the time that I have right now. So I'm just going to state this here. This is about the matrix infinite series when less divergence. For matrix A, C project, the following statements are equal to. First statement is this infinite series I plus B plus A squared, etc. Is convergent. That's the first statement. Now this is like 1 plus x squared, binomial series. And the subseries converges when mod x is less than 1. The radius of convergence is 1. The domain of convergence is -1, 1, open both sides, -1 part. We have something similar, which is that the spectral radius of the A is less than 1. We also have the other condition, which we have learned when we studied series first. The nth term of convergence is supposed to be limit K tends to be into the D. The series is convergent and the nth term is supposed to be this. So this is not new, but these two are. And in this case, meaning that if any of the statements is true, then I minus A is invertible. And in fact, one has this binomial expansion type formula for I minus A because summation A equal to 0 to infinity A to the this is 1 plus x square, etc. Of infinity. The power series of binomial series is convergent when mod x is strictly less than 1, and this series represents 1 by 1 minus x in the interval mod x less than 1. And so that's this result. And the proof mainly relies on the Jordan canonical. You have to look at the Jordan canonical form, then manipulate. So this is something that I'm going to make use of. Again, the reference for this is you can look at Mayer's applied in the science publication. Okay, how is this going to be used? I'm going to prove first Vedant theorem. Vedant theorem for positive matrices. Vedant theorem for positive matrices. Positive matrices here. So A is a real matrix. Has the property that all its index are positive. So this takes us back to the non-negative matrices that we started. This means that all index are positive. This means all index are positive. For a non-negative, A is non-negative if and only if ARn plus is contained in Rn plus. So how do you characterize positivity? Similar to that. Of course, ARn plus is contained in Rn plus because this is more than non-negative. Strictly contained. Yeah, strictly means what? A of interior Rn plus is contained in interior Rn plus. That's what this is. ARn plus contained in Rn plus is weaker. The stronger form, which is applicable for precisely for positive matrices, that A interior Rn plus is contained in interior Rn. Okay, so that's the positive matrix. See, if A is positive, you know what the speculator is. Maximum of the absolute values of the eigenvalues of A. Now, a positive matrix may have complex eigenvalues, so that is not a problem. So look at the spectral radius. The claim is that the spectral radius is positive. A is positive. The spectral radius is positive. How do you prove this? The spectral radius is the maximum of the model A, so it has to be non-negative. So only other possibility is that the spectral radius is 0. If the spectral radius is 0, spectral radius by definition is the maximum of model A of the eigenvalue. So it's non-negative number. If it is 0, then look at the Jordan canonical form of A. Look at the Jordan canonical form of A. So what is the Jordan canonical form of A? See, Jordan theory is complicated, but Jordan canonical form you can immediately write it down. What is the size of the block? What is the number of blocks? That is part of the theory. But what is the Jordan canonical form of a matrix? It is consisting of Jordan blocks. Each Jordan block has the property that the diagonals are the eigenvalues, and the super diagonal entries are non-zero. Okay. Now, if the spectral radius is 0, what it means is that 0 is only eigenvalue. Radius is 0, 0 is only eigenvalue. Okay. So the diagonal entries are all 0. Super diagonal entries block-wise they contain 1. So they are important. Right? Take a matrix of the type 0, 1, 0, 0. For example, this is an important matrix. Its square is same. Jordan canonical form. The diagonal entries are 0. Off diagonal entries are no matter what they are. Some power. Each of the Jordan blocks is 0. Maximum of all those. It will give you the Jordan canonical form of A. These are the important matrices. The Jordan canonical form is important. This implies the nilpotency will not change under similarity transformation. Jordan canonical form is a similarity transformation for the matrix A. Right? A equals P, J, P equals. J is the Jordan canonical form. It doesn't change under the eigenvalues remain the same. So this means that A is also important. That's not possible because the entries of A are positive. So the entries of any power of A will also be positive. This is not possible. And so the spectral radius cannot be zero. It has to be positive. Okay, so fill up the radius here. So spectral radius of A is positive. Now spectral radius of A is positive, and also observe that if you look at A by rho of A and take the spectral radius of that matrix. This is simply 1. And so we can assume without loss of generality in the rest of the discussion that given positive matrix, the spectral radius of A is 1, just for simplicity. You replace A by spectral radius of A and whatever happens. And remember that we have Perron theorem concerns the existence of a special eigenvector corresponding to a special eigenvalue. Eigenvector, they remain invariant when you divide by a constant. So this won't make a difference. This is just thing for simplicity. Perron theorem is about eigenvalues. So we hereafter assume that for a positive matrix A, the spectral radius is 1. Then this is what we have. What is the first statement of Perron's theorem? First statement is that so A is positive. We then have the first statement is that the spectral radius of A is an eigenvalue of A. Spectral radius of A is an eigenvalue of A. Second statement is that, see, Perron probability theory, if you look at this book, Applied Algebra, it runs to several sections. I'm only highlighting the most important aspects of it, especially the ones that we will make use of in the rest of today's discussion. The spectral radius is an eigenvalue. There is no reason why the spectral radius should be an eigenvalue for any matrix, but that's true for a positive matrix. Not only that, there exists then positive such that Az equals rho A constant. There is an eigenvector associated with the dominant eigenvalue. This is spectral radius. This eigenvector has the property that all its coordinates are positive. Now this is underlying the PageRank algorithm. Google's PageRank algorithm. Google's PageRank algorithm applies to a non-negative matrix. This result is for a positive matrix. But for a non-negative matrix, you need one little extra condition. The notion of irreducibility that will guarantee that these two statements are recovered for a non-negative irreducible matrix. That is Perron-Frobenius theorem. Let's look at Perron theorem. This is that statement. There are other aspects. For example, I just rewrite B as the D prime. There is a unique vector. We call that as that by B, call that as a Perron vector. There is a unique vector P such that AB equals vector radius of A into P. The one norm of P is 1, of course P is positive. All that you don't take such a vector, divide by the one norm of that, you get such a unique vector. It is unique to something that you need to prove, but I will not get into that. That's a consequence of B and the little work. The main aspects are these two. The spectral radius of a positive matrix is an eigenvalue of that matrix. You can associate, see, the multiple of an eigenvector plus an eigenvector, so you can take a negative multiple of say, so statement that can associate a positive eigenvector corresponding to that positive eigenvalue. There are other aspects. For instance, this eigenvalue is algebraically simple. This is the only eigenvalue that's a root of the characteristic polynomial actually. Root of the characteristic equations. So there is a bit of theory there. What I will do is just prove the first two parts here. Look at the case when Frobenius extended this result to non-negative matrices. Define an M matrix. Link the M matrix notion to what the matrix classes that we have considered earlier, and then give an application
to the convergence of the Gauss-Seidel iterative scheme. Okay, so just to tell you that these are all different things related to the one. There's one big picture, and we are just looking at parts of it. Okay, so how does one prove? We already have so without loss of generality, speculated is always equal to 1. Let's start with an eigenvalue eigenvector equation. Start with A with lambda. X is possibly complex. Lambda is possibly complex. Look at Ax equal to lambda. This is an eigenvalue eigenvector equation, so x is not 0. I will reserve this notation mod x to be the vector whose coordinates are the absolute values of the coordinates of the vector x. Modulus of a vector, not norm of a vector. Norm is a number, modulus is again a vector. So this is how I define. Then start with, so we are assuming that mod lambda equals 1. We assume that mod lambda equals 1. Now look at 1 is the speculative entity. Now look at mod lambda mod x. This is mod lambda is 1, so this is simply mod x. This is mod lambda x. Lambda x is ax. What is modulus of ax? Modulus of ax works like you can use a triangle inequality here. Ax is a vector, column vector, and it's a dot product of the rows of A with the column vector x. And so you can verify that triangle inequality code. This is less than or equal to mod A mod x. I'm asking you to verify these things. Modulus is a new operation, perhaps. But A is positive, so this is A mod x. A is positive, so all the entries of so modulus of A is equal to A. I will define this A mod x to be set, a vector set. I'm defining A mod x. It's a column vector, I'm defining that, denoting that by set. Observe the following. A is a positive matrix. X is a non-zero vector. If you look at modulus x, it may have some zero coordinates, but all coordinates are non-negative. Modulus x has all its coordinates non-negative. Some coordinates may be zero, not a problem. All coordinates of mod x are non-negative. I am multiplying a positive matrix by a non-negative vector. All entries positive non-negative vector. The resultant column vector will have all its entries positive. No coordinate of the resultant vector can be zero, because at least one coordinate of this vector is positive. At least one coordinate of mod x is positive, because x is not non-zero vector. So multiply a positive matrix with a non-zero vector, non-negative, non-zero vector. The resultant is a positive vector. All coordinates positive. So for one thing, Z is a positive vector. Z is a positive vector, and let's now denote y and y has z minus mod x. So I'm defining a new vector y, that is z minus mod x. Z minus mod x is the whole argument tells me that this is non-negative. This is non-negative. We want to show that y is 0. We are done. If you show y is 0, we are done. What is the reason? If y is 0, then this whole thing is an equation. This inequality goes. So a mod x equals mod x. A mod x equals mod x. Now look at mod x. Mod x on the right, if you claim y is 0, what happens if y is 0? So we just write that y equal to 0 tells us that a mod x equals mod x. Now look at what we have here. A positive matrix, non-negative vector, resultant is a positive vector. All coordinates of x must be positive. This is the vector that I am seeking. I am done. If you prove this, then this is what you will show. See, that z is different from this z. This one. So if you want, I can change this to u. So I can just take u to be mod x and this proves two things in one shot. The spectral radius is an eigenvalue, and an eigenvector can be chosen if an eigenvector corresponding to the spectral radius can be chosen in such a way that each of its coordinates is positive. So this is the claim. The y is 0. But observe that y is non-negative. That's here. You already noted that y is non-negative. If y is not the zero vector, so if it has at least one positive coordinate, then we have the form. You want to show y is 0. We know that y is non-negative. So if it is a non-zero non-negative vector, see, I will write it usually. It's non-zero non-negative. We want to show that y is 0. Okay, so let's just make this calculation. For one thing, y is a positive vector. For the same reason, A is a positive matrix. Y is a non-negative vector with at least one non-zero coordinate. So the product AY is a column vector that all its coordinate is positive. AY is positive. We also have Z positive. And let's also make this calculation for AY. What is AY? AY is A Z minus mod X. So okay, Y is Z minus mod X. So this is AZ minus A mod X. This is AZ minus Z. A mod X is Z. And so this is A minus I acting on Z. So AY is A minus I Z. Okay, now look at these two. You can do a comparison between the coordinates of the AY and the Z. And you can make a component-wise comparison to show that there exists an epsilon positive such that AY is greater than epsilon Z. So what is it that we have done? You know that AY is positive, you know Z is positive. It is like, all coordinates are positive. So I can do a coordinate-wise fraction and take the maximum. Maximum? Yeah. Take the maximum. Epsilon with the maximum, and that epsilon will be positive. Maximum of positive quantities is positive, and that is satisfied. So AY is greater than epsilon Z. AY has been calculated to be this. So I have A minus I Z to be greater than epsilon Z for some epsilon positive. So this gives me. So you push this Z to the other side, it becomes epsilon plus 1. So if you look at A by 1 plus epsilon, the action of that on say this to be greater. This is what you take here. Now all this matrix is let's say so I have C Z greater than Z, where the spectral radius of C is the spectral radius of A by 1 plus epsilon. That's 1 by 1 plus epsilon, spectral radius of A. Spectral radius of A is 1. So 1 by 1 plus epsilon less than 1. Spectral radius of C is less than 1. C is a positive matrix. Spectral radius C less than 1. The theorem that I wrote down just now tells me that limit A tends to C to the A is 0. Look at what you have for the matrix. Go back. Yeah, we have C Z equals C Z greater than Z. Which means that C squared Z is greater than C Z plus greater than Z. And then C to the K Z is greater than Z for all the. This is any matrix inequality. I hope that's clear. See, this is if C Z greater than Z, it's not in general true that the C square Z will be greater than C Z. In general, it's not true, but C is a positive matrix. And so for positive matrices, it is true that X is greater than or equal to Y implies Cx is greater than or equal to C. C is positive. Non-negative is enough. And so we have this. Now take the limit as K goes to infinity. will have Z is not a contradiction because it has all its coordinates also. Contradiction comes from the assumption that AY is positive. Comes from the assumption that Y is a non-zero term. Even if Y has one non-zero component that is positive, and then the whole thing applies. And so Y has to be zero. Y0 tells us that there is Y0 tells us that the second one. It proves both that the spectral radius is an eigenvalue, and you can associate a positive eigenvector corresponding to the spectral radius. This is Perron's theorem. Perron's theorem for positive matrices, and this has lots of applications. What is much more applied, more relevant to many of the problems is when you look at considerations involved in a non-negative. If you allow some entries of A to be 0, then what happens? This is typically the Google space rank thing. That is the C matrix of a graph. Has entries 0 and 1. Symmetric matrix has entries 0 and 1. So when about the instance of the adjacency matrix of the graph, the graph corresponding to the dictate is associated with a set of keywords that is obtained. Supply a set of keywords. There is immediately a network that is formed, a graph, a directed graph, a diagram that is formed from the set of keywords. It lists those pages corresponding relevant to the set of keywords. What you get is a directed graph, a diagram. So how is a diagram defined? See how is given a matrix A. Given matrix A, how is a diagram defined? You know that. So how is a diagram defined? The number of vertices of the diagram is the same as the order of the matrix. And two vertices V1 and V2, there is an edge from V1 to V2, it's a diagram. There is a directed edge from V1 to V2 if so there is a directed edge from Vi to Vj if Aij is non-zero. The graph A may have the property that Aij is non-zero, but Aj is 0. That's possible. So with this definition, you get a digraph corresponding to a matrix A. So you generate a matrix A, there is a digraph. For a digraph, you ask the question as to whether it is simply connected, just connected or strongly connected. Weakly connected, strongly connected. Weakly connected if there is an edge, it's a path at least in one direction. That is weakly connected. Strongly connected, there is a path, there is a directed path between any two words. That is strongly connected. If the graph is strongly connected, then the matrix A is said to be an irreducible matrix. The matrix A corresponding to which you drew the graph, that matrix is called irreducible. If you have a non-negative irreducible matrix, Perron's theorem, first two aspects carry over. So I have told you a lot of things because I didn't want to repeat those. Let A be non-negative and irreducible, then Perron's Frobenius theorem. Yes, right. Again, the spectral radius has to be positive. See, a non-negative matrix can have spectral radius 0. Give an example, neighborhood matrix. The Jordan form where the diagonal entries are 0, super diagonal entries are 1, that's non-negative matrix. Spectral radius is 3, it's an important matrix. So a non-negative matrix may have spectral radius 0, but if the moment you get irreducibility, it can be shown that it can't be 0. Spectral radius has to be positive. Spectral radius is positive, that's the first aspect. Spectral radius is an eigenvalue. And the second thing is about a vector u positive such that AU equals rho A. Corresponding to this, there is a Perron vector. So the main properties of Perron's theorem can be recovered if the matrix A is not merely non-negative, but also non-negative but irreducible. So irreducibility is important. Irreducibility is dictated by the graph theory condition that I mentioned just now. Now you can construct easy examples to show that a non-negative matrix, as I told you, take an important case, speculated can be zero. It may not have a positive eigenvalue. It may not have a positive eigenvalue. The speculated can be zero. So there may be only a non-negative vector that belongs to the null space of A. The algebraic multiplicity may not be one. So construct those examples. But this is the thing that tells you that Perron theorem carries over the non-negative matrices together with this assumption of irreducibility. As I mentioned, this is a huge theory. How this is extended to other cones, etc., nonlinear operators, etc. It's a subject of intense research. There is also something called the Iclaa formula, but I'm going to just give you this one. This is a consequence. Let A be a non-negative matrix together with a positive vector is. If direction R, of course, R is non-negative, such that Ax is less than or equal to Rx, then you can show that the spectral radius of A is less than or equal to R. One is interested in obtaining estimates for the spectral radius. By the way, one of the ways of getting a dominant eigenvalue is the power method. It's a Iclaa subspace term. You keep computing the powers of A applied to a vector, it converts to an eigenvector corresponding to the dominant eigenvalue, and you can also separate out the eigenvalue. This gives an estimate. This gives an estimate upper bound, similarly a lower bound. This gives an estimate for the spectral radius if you can figure this out, if this happens. We make use of this is a consequence of what is called as. This result is obtained from what is called as a Collat's Iclaa formula. The consequence of Collat's Iclaa formula. We make use of this in our final application of Perron theorem. Okay, let this remain. We are now interested in the following problem. Looking at matrices which have the following sign pattern. A matrix A with a real entries is called a Z matrix. It's called a Z matrix. I gave this definition earlier. If the off-diagonal entries are non-positive, just asking for recall. If the off-diagonal entries are non-positive. Matrices of this type are used in many applications, input-output economic models in a closed economy, finite difference method applied to solve numerically differential equations, etc. So this occurs in more ways than you can imagine. Such a Z matrix is called an M matrix if it has the following property. Or M matrix. See, I don't know the Z. I think it's a German now, but I don't know that. I know this M is in Minkowski. I'm not Minkowski. The name of mathematics. So he considered a strictly diagonally dominant matrix coming out of a certain spanning difference approximate apply to a certain problem. The quotient matrix is the Z matrix. It's actually a tridiagonal Z matrix with the property that it is diagonally down, strictly diagonally down. He showed that in that case, the inverse strictly diagonal matrices, strictly diagonal matrices, the inverses. He showed that the inverse has this property that all its entries are common. So we are coming back to this problem. The matrix A is monotone. A is non-negative implies it's non-negative. So he got it. So this is what he considered, and Ostrowski extended Minkowski's results, and he was the one who gave the name M matrix. So a Z matrix got an M matrix. If it is invertible and the inverse is non-negative. So whenever we write A inverse non-negative, we assume that A is invertible and that the inverse has this sign power. All its entries are non-negative. So how do you characterize? A Z matrix can be invertible, and the inverse can have all its entries non-positive, negative, etc. That's possible. A Z matrix. So you can try to construct a very simple example. A Z matrix, which is invertible, can have the property that the inverse is non-positive. All entries are less than or equal to C. They are asking for all entries to be greater than or equal to C. When does this happen? So here is the characterization. Let's make the following observation. If A is Z, then we can write A as x prime prime to T minus B, where B is a non-negative matrix for some scalar S. Any same matrix can be written as a difference in this manner, Si minus B, where B is entry-wise non-negative. Now look at what you have here. The contribution to the off-diagonal entries of A, the contribution comes only from the second term. The first term is only diagonal, S times diagonal. First term doesn't contribute anything to the off-diagonal entries. It's only the second term that contributes. So each of the matrix B, each of the entries of B is non-negative, so you get a negative sign here. So the off-diagonal entries are non-positive. Any Z matrix can be written in this manner for some S and for some non-negative B. All that we have to do is speak the S such that Si minus A is non-negative. Si minus A is non-negative. Call that matrix as B, then A equal to Si minus B, and with the B non-negative. So B such that Si minus A is non-negative. There are many choices for that question. How does one characterize that matrix in terms of this? We have the following. That A being the Z matrix. So I use this notation. Okay. Then A is an N matrix. Equally. So you need a connection between the two terms that you have, the number X and the matrix B. What connection is relationship is S greater than specific radius, strictly greater than specific radius of B. So here again the specific radius comes. You have a non-negative matrix. You are seeking a number that's greater than the specific radius of the non-negative matrix. If A is trivial, if A is S times identity, then the matrix B is 0. In this case, specific radius is 0. But that's the trivial situation. The coefficient matrix doesn't will never look like the multiple of the identity. You're solving a real life problem. So this again, assume without loss of generality that this B has a property, specific radius B is positive. So this is an something condition for a Z matrix to be an N matrix. Okay, I'm going to do the proof. You will see how easily it comes from the previous substitution. Let's take the necessity sufficiency function. Suppose that S is greater than the specific radius of B. The B is non-negative, I remember that. Then specific radius of B by S is less than 1. I appeal to the theorem that I wrote down. If specific radius of A is less than 1, then I minus A is invertible, and then the inverse has that binomial series for expansion. I minus BS is invertible, I'm making use of that theorem. So I minus d by x inverse is summation k equals 0 to infinity d by x to the t. I am applying a from that theorem to d by x. Now, what is the extra thing that you have here? Let's first simplify this. This is s into I minus, I'm sorry. This is s into si minus b inverse. Okay. To take 1 by s and then take that outside. To multiply throughout by s. Then this is okay. So this is what we have on the right hand side. This matrix is identity plus b by x plus b by x squared, etc. Where each each coefficient, each term is non-negative. So this is a non-negative. We're adding the non-negative matrices to the identity. Every step these are all non-negative. So this is a non-negative matrix. This is S into A inverse. No? So this is S into A inverse. In particular, we have A inverse is non-negative. So this was the easy part. If the sweating radius of P by S is less than 1, then I minus P by S is invertible, and the inverse has all its identities non-negative. Just a multiple of the matrix A, S into 1. This is 1 by S into A inverse. This is 1 by S into A inverse. S is possible. Sweating radius might be 0, but S is possible. So A inverse is non-negative. And so you have this same matrix with the property that the inverse x and the inverse of the y is non-negative. So the matrix A is an M matrix. What about the converse part? Converse part, we need to show that. So what do we need to show? You see all this is the converse part. Converse we like SI minus B. The invertible and the inverse is non-negative. A inverse and A inverse is non-negative, that's the converse part. We need to show that. S is greater than the square base. What we need. That is, to take any eigenvalue of B, you must show that the modulus of the eigenvalue is less than x. Okay, start with the eigenvector. Take dx equals lambda x. X not equal to 0. We need to show that mod lambda less than s. Okay, let's do the calculation. It's very similar to what we did earlier for the around there. Start with mod lambda x. First mod lambda mod x, and keep this on one side. This is also mod bx. Mod bx is less than or equal to mod b mod x. B is a non-negative matrix, and so this is b mod x. So if you combine these two, you get mod lambda mod x is less than or equal to b mod x. And so if you look at S minus mod lambda of mod x, see this will be, so when you take a minus here, it goes the other way around. So it's greater than or equal to S identity minus B mod x. Or you multiply this by minus 1. So minus mod lambda mod x is greater than or equal to minus b mod x. That's the second term. I'm also adding the s mod x. I'm adding s mod x. So I get this. What I know is that I know this. What I know is that si minus b is invertible. And the inverse is non-negative. So I can make use of this. So this tells me that mod x it's always greater than or equal to all the coordinates are non-negative. And it is less than or equal to. I am multiplying this, pre-multiplying this equation by Si minus B inverse. Inequality will remain because Si minus B inverse is non-negative. So this is again x greater than or equal to y, a non-negative implies Ax greater than or equal to equal. If x is greater than or equal to 0 and a inverse is non-negative, then a inverse x is greater than or equal to 0 is what I am doing here. So mod x is goes to the other side. Si minus, so the number comes out first. Si minus inverse mod x is what I have. Now look at what I'm mentioning. This is a non-negative matrix together operating on a non-negative vector. So this is non-negative. Okay. And on this side you have non-negative. So this number has to be non-negative. So look at x greater than or equal to mod lambda. You want to show x is strictly greater than mod lambda. But see what happens when x is equal to mod lambda. When x is equal to mod lambda, the left hand side is 0. When x is equal to when x is equal to mod lambda, the right hand side is 0. Mod x is sandwiched between 0 and 0. So mod x is 0. Mod x is 0 can happen only when x is 0. But x is a non-zero vector, an eigenvector. And so this s cannot be equal to mod lambda. So mod lambda less than s is what we wanted to show. We took an arbitrary eigenvalue corresponding to an arbitrary eigenvalue for the matrix V. We've shown that the magnitude of that doesn't exceed s. Is what we want to show. S is less than the speculative of V. Yeah. Yeah, so what is the thing? This one is non-negative. That is fine, right? Yeah. This is non-negative. This is non-negative, so this number has to be this is a number. This number has to be non-negative. But it can't be 0 because that will give a contradiction. Due to the fact that x is 9. So this is an M matrix. So what is an M matrix? An M matrix is a matrix, meaning a matrix having off-diagonal entries non-positive, invertible, inverse being non-negative. So an M matrix is a Z matrix. This is also monotone in our terminology earlier. Z matrix A is an M matrix. When the weight is it is monotone. When the weight is monotone. Just recalling what monotone is mean. A is non-negative, implies x non. This is monotone. So this keeps coming again and again. You do different things. You come back to what we started. I write down a theorem. This theorem typically has some 60 equivalent conditions. I am just going to write a few. Okay. This will kind of summarize what we did so far. Some parts of this theorem have been proved wrong. So, what is this master theorem? You can refer to Bergman for example. Non-negative matrices in the mathematical sense. Like A, B, or B matrix. Then the following statements are equal. First one is A is one. Okay. A is a flow matrix. Third, A inverse exists. And A inverse is non-negative. Such a thing is called inverse non-negativity. A is inverse non-negative. Inverse exists and the index of the inverse are non-negative. Statement B, A is a B matrix. What is the B matrix? All principal minors are positive. All principal minors are positive. And the matrix of the P matrix. P matrix, the context of P matrices is from univalence theory, but its relevance goes beyond univalence theory. For example, in linear complementarity problem, for every Q, LCP gamma Q has a unique solution. That's the P matrix problem. So A is a P matrix. Statement D. Direct exploits terms considered A is possible. I never spoke about this. Direct text possible is that A is possible. See, if A is inverse non-negative, look at condition C. If A is if A inverse exists and A inverse is non-negative, then this follows immediately. Get it right? A inverse is non-negative, then the X positive such that AX is positive. Such a matrix is called an S matrix. S matrix is also called linear complementarity. Any Q matrix is an S matrix, but there are S matrices that are not Q matrices. So I wanted to just write this the next couple of minutes because it will take only that much time. Statement C implies E. Give an example to show that statement E holds, but the matrix is not even equal. So you need the C condition. You need the C condition. On the other hand, A and C are equivalent for any matrix. No C condition. A and C are equivalent for any matrix A. No C condition. So can you write this now? A inverse non-negative implies A is less matrix. There exists X possible such that A is possible. Use one of the properties that I mentioned just now when we were discussing. I mentioned it twice or thrice. You take a non-negative matrix and a positive vector, or a positive matrix and a non-negative vector. The product is a positive vector. The product is a positive vector. So you have the proof. Okay, so what how did you? Yeah. Okay. No, you want to show that it's X positive. Yeah, such that AX is positive. You want to show the existence of positive X such that AX positive. Yeah, so what is the choice for X? What is it? But only for parameter. Okay, you take parameter. See, take any positive vector. Take any positive vector. Take E for example. Take E and look at A inverse E. Now A inverse cannot have a zero row because it's inverted. So each row has a non-negative entry. So A inverse E is a positive vector. Call that as X. you're done. A inverse E, you call that as X. Then X is positive and the AX is E, that's positive. So that's easy. Converse. Give an example of a 2 by 2 S matrix, which is not invertible. Two by two S matrix is not invertible. What is an S matrix? Their X positives are the AX positives. Very, very flimsy. Easily constructed. Can easily constructed. So what is one such A? All into one. All into one. You're done. All into one. Take any non-negative vector that will work. All into one. Take any non-negative vector X. Then into one X positive, right? So take all the entries one. Then A into E X positive. So this is true. But all entries one is rank one, not invertible. So you need this recondition to go back. So we are talking about equals. So what does it mean? If you have an S matrix, it is in general not invertible, but it is invertible and the inverse is non-negative. If it's also a C matrix, so if it has that sign structure, then its inverse is and its inverse is a non-negative matrix. What are some other conditions? F. All entries, all diagonal entries of A are positive, and select this a diagonal matrix. There is a diagonal matrix D with positive diagonals. There is a diagonal matrix D with positive diagonals such that the matrix AD is strictly diagonally down. Diagonally down. A is strictly diagonal, AD is strictly diagonally down. A may not be strictly diagonally down, but this is as good as being strictly diagonally down. All you have to do is to just scale the diagonal entries by the matrix T. AD is strictly diagonally down. This is another condition. You know, I could LU decomposition is it's a very nice tool to solve an equation by a direct method as against an iterative method like Gauss-Jacobi or Gauss-Seidel. LU method is a direct method. What is the direct method? A can be written as L times U, where L is lower triangular, that entry is 1. U is upper triangle. So A is equal to B can be reduced. If you can reduce A using this LU decomposition, then you can solve A is equal to B by two systems. One is obtained by backward substitution, the other one is forward substitution, which are easier to solve. So you break the problem into two subproblems and you solve the two subproblems easily, more easily than the combination will be much easier than solving A is equal to B directly. That's LU decomposition. The question arises as to which matrices have LU decomposition. Any answers? Which matrices have LU decomposition? There is one result, one sufficient condition coming from Gaussian elimination. Assume that the matrix A is invertible. If you can reduce the matrix A to its row reduced echelon form completely by elementary row operations of the first type. You allow for you don't allow for row interchange. The rest of the two operations are okay. Don't allow for row interchange. If you apply the rest of the two operations, that is multiplying your row by a non-zero scalar and adding a row of a matrix to another row so that you make those entries pivot rows, for example. You allow for only these two operations, and then if the matrix A has a logicity, that you allow for only these two operations in the elementary row operations to reduce to the probability form. Such a matrix at the end of this process you can show has LUT approach. There is another product, another set of sufficient conditions, which is that all principal minors are non-zero. All principal minors are non-zero will imply that A has an LUT approach. These are some of the sufficient conditions. Okay. Now look at the matrix A. It's an M matrix. It's an M matrix. It's also a P matrix. And all principal minors are not just non-zero; they are positive. All principal minors are positive. So you can apply this result. A has an LU decomposition. So A being an M matrix has an LU decomposition. You can also go the other way around. A can witness LU. L is lower triangular. Q is upper triangular. Such that you also have something extra. Both L and U are M matrices. Both L and U are M matrices. The product of two M matrices is not in general in M matrix. The product of two M matrices in general not an M matrix. So it's a very special situation. So what it says is that A is an M matrix. Then for one thing, A has a LU decomposition. For another, both the factors are also M matrices. Conversely, if A is a C matrix, having the property that it has the LU decomposition, then A is an M matrix, and each of the factors is an inverted M matrix. So you have both ways to happen. So this is another thing, which is purely a numerical linear algebra kind of a thing. And others. There are many more. I just wanted to highlight a few. So there's a numerical linear algebra connection coming from here and here. There's a linear complementarity coming from here and here. This is purely linear algebra order theory. A inverse X is A inverse non-negative. So these are linear algebra order theory. And what I have done is to only look at Rn plus. You can ask the questions to a general form. You can ask these questions to a general form. Okay. That's the subject of some research papers. If you write to me, I can tell you what those are. I will not force it upon you now. When you change the, even for Rn with the Lorentz curve, some of these results are not true. Perkas lemma is not true when you change Rn plus to the Lorentz curve. So you can't expect this equivalence to carry over in a very general situation. Okay. So that's what happens when you go from Rn plus to a general form. Okay. Now to summarize, I have the following result. Any questions? Let's go back and look at the form. There are, see, we are looking at these two iterators, Gauss-Jacobi, Gauss-Seidel. Gauss-Jacobi, Gauss-Seidel both converge when A is strictly diagonally down. Gauss-Seidel converges when A is positive definite. A similar conclusion is not true for Gauss-Jacobi. But for Gauss-Jacobi, there is a few conditions, which is A and 2D minus A. If A and 2D minus A are positive definite, then Gauss-Jacobi converges. There is another situation where both these converge. That is for M matrix. Let A be an M matrix. There is only one limited condition. Consider Ax equal to B with the B non-negative. This condition can be relaxed a little bit, but I confine my attention to this case. B is non-negative. B is, see, in any problem when you formulate a system Ax equal to B, This A is the coefficient matrix, B is the requirement vector. Requirement coming from an economics problem. A requirement is always non-negative. So this is typically applicable when you're looking at problems coming from economics. D will be the demand vector or the supply vector, something like that. So this right hand side will always be non-negative in such problems. For such problems, both Gauss-Jacobi and Gauss-Seidel methods converge. That is the semantics theory plus Perron rule. Okay, so I'll just highlight that. What is see, let me look at Gauss-Seidel. Gauss-Jacobi is even easier. For Gauss-Seidel, what do you have? You have A is L plus D plus U. See, remember A is an M matrix, right? And so A is a C matrix. And A is a C matrix plus monotonic setting. I will make use of this condition. Plus then exists X positive. That is why I wrote that equivalent condition. There exists X positive such that A is positive. So I use these two. C matrix sign factor of diagonal is non-positive, and the fact that A is an S matrix because A is an N matrix. So I'm using the equivalent condition. Okay, so you write A as L plus D plus U, and what is Gauss-Seidel? It tells you to pick this as N and this as N. That's the splitting. And so what is the iteration matrix here? The iteration matrix minus M inverse, that is L plus D inverse into this iteration matrix for Gauss-Seidel. Why is L plus D invertible? We need to confirm that L plus D is invertible. Okay. At this stage, we don't know. Okay, is this valid? That's the first question. But let's go back and see what we have here. See, there is this X positive, so the A is positive, right? First observe that the L and the U are both non-positive. Because A is a C matrix, off diagonal entries are non-positive. Off diagonal entries are done by L and U. L is a lower triangular part, U is upper triangular part. So these are non-positive matrices. And what do we have? There is X positive such that AX is positive. AX is L plus D plus U of X. This is L plus D X. So it's a plus. That L plus D operating on X is equal to AX minus UX. AX minus UX. Now U is a non-positive matrix. So minus U is non-negative. AX is positive, so this is positive. Okay. You can call this L plus D as some S. Sx positive with the X positive. A is L plus D plus U, lower triangular, diagonal, upper triangle. That's the splitting. And then you introduce the Gauss-Seidel splitting, which is lower triangular part, upper triangular part separate. Lower triangular part taken together. And so what do we have? L plus D is this S. What is S? This S is D matrix. Is S a Z matrix? Yes, of course. It is lower triangular part plus the diagonal part of the matrix A. So it's a Z matrix. Non-positive. Off diagonal are non-positive. I have a Z matrix which satisfies condition E. So this Z matrix must be an M matrix, but it's invertible for one thing. So if this is valid. L plus D is invertible is valid. So this makes sense. So this is right. It's valid to write H in this line. So this is a splitting according to the definition. A splitting is writing it in this manner that the first term is inverted. So this is a splitting. I want to show this particular as H is less than 1, right? Now look at I want to use the Collatz-Taylor formula. So I want to look at H6 first. So what is the iteration C? what's the equation? See, you have L plus the inverse U x plus the L plus the inverse of B. That's what the fixed point equivalent calculation of Ax equal to B is this. Now look at what you have here. So this is Hx plus C. This is the notation that I use. Where C is this vector, L plus B we have shown is an invertible L matrix. B is non-negative. An invertible L matrix is non-negative. The inverse of an L matrix is non-negative. So this vector C is non-negative. X equal to H plus C. H is a iteration matrix. C is this vector. When you write the splitting, you will write this as M into I minus M inverse. Okay, this is not what we have. So this will give me Ax equal to B equal to Ax plus Mx minus Nx. And then you push Nx to the other side. You have X equals M inverse Nx plus M inverse. This is clearly what I would thought. M is M plus B and N is minus B. That's the splitting. This is the fixed point. This suggests that fixed point should be same as this. So C is non-negative. So what do we have? See this X now can be taken to be that X positive. There is X positive such that Ax positive. I pick that X. For that X, I have this. So this tells me from here, this tells me that Hx equals X minus C. C is non-positive, so this is strictly less than X. Hx is strictly less than X. And Hx is, I want to apply Coulomb Fourier theory. Coulomb-Shannon formula. If, so what is the Coulomb-Shannon formula? If R is non-negative, X positive, such that Ax is less not equal to R, then I can conclude that the special radius of A, of course, A is non-negative. I can conclude special radius of A is less than or equal to R. I have Hx less than X. I have Hx less than X. H is non-negative. How? H is non-negative because minus U is non-negative. U is non-positive. So minus U is non-negative. L plus D is an inverse L matrix. So L plus D inverse is non-negative. So H is non-negative. Hx is less than X. And in this implies that the speculates of X is less than 1. So see there is a less than or equal to here. By continuity you can check. So this is Perron-Frobenius theory at the last step. So you need M matrices, Perron-Frobenius theory to show that Gauss-Seidel method for an M matrix is convergent. A little more simpler calculation will give you a proof for the Gauss-Jacobi. But I want, and see, this is a statement writing down characterizations for a Z matrix to be an M matrix. When is a Z matrix an M matrix? This is a question of relating to several combinations. So this is just a partial list of those results. A Z matrix is soft diagonal negative, non-positive. I want to know when it's an M matrix. There are various ways of verifying it. These are those ways. So I want you to just check those calculations here. Gauss-Seidel method for an invertible M matrix, right hand side non-linear. That's also an assumption that we are making. It is not really required. You can relax it a bit, but I'm not getting to that. A is an M matrix, Gauss-Seidel method, right hand side non-linear. Typically applicable for problems in economics. it is converted. Minus E. There's a minus E. The iteration matrix is minus, the iteration matrix is the inverse n. And so n is minus U. N is minus U. So this last part is Collat's variant formula for a non-negative matrix. This is result which I wrote down earlier. Okay, so I think I'll stop here. And I hope you had some exposure to non-negative matrices in relation to the complementarity problem, numerical, in algebra, etc. So, any questions? I'll try and answer. Any question?
If they are other class this in the I think about so.
That is okay.
If they are other class this for which we can guarantee for convergence or other than it's sure.
I think SOR also will work. There will be some condition on that omega. Yeah, I haven't tested that. How much of this can be recovered in the case of the general code, even over planning time? That's one question. How much of it recovered means how many such similar statements can be written on for a general code, non-polynomial, like the Lorentz code. Yeah, any question? Any means any. Quantity and also different from.
Definition.
The definition is primary, just AP is contained in P, P is the code, that's all. You can apply it to a linear operator, non-linear operator, quantity here, that's a definition. Positive means it leaves the code in there. So there's no problem with the definition.
Can you do rectangle matrix?
What?
Rectangle matrix. So instead of eigenvalues that it takes single value.
See, rectangular matrices, you can't talk about eigenvalues, you can talk about singular values. So you want A transpose A to be non-negative. You want A transpose A as well as A transpose to be non-negative. It's possible. Without A being non-negative, can have A transpose A as well as A transpose being non-negative. That's possible. You can apply the round for this. Okay. What does it say about the matrix? Say I don't. Let's go to singularity decomposition on that. See, the problem with singularity decomposition is that it will destroy the non-negativity structure. Non-negativity is very special. A mild perturbation will. So it may not be a good idea to combine those things. Yes. Okay, so thank you.
नया पड़ा है नया पड़ा है क्या? हाँ तो बस चल है ना चलो चलो चलो
थोड़ा इसने ये क्या है मैं आ रहा हूँ
हाँ हाँ हीरो